the scientific revolution in astronomy began not with a new idea, but with new data. Tycho Brahe, working from his island observatory from the 1570s, built large, meticulously calibrated naked-eye instruments, great quadrants and sextants of brass, and with them measured the positions of the planets and stars to an accuracy of 1 or 2 arcminutes. That was 10 times better than any predecessor before him, and close to the very limit of what the unaided human eye can resolve. His catalogue eventually recorded the positions of 777 stars at this precision, and most crucially of all, decades of patient, nightly positions for the planet Mars. Tycho himself favoured a hybrid model in which the planets circled the Sun while the Sun circled a motionless Earth. But his true and lasting gift to science was not his theory, it was the data. When Johannes Kepler inherited those Mars observations, after Tycho's death in 1601, he confronted a problem the data made utterly inescapable. Mars has the most eccentric orbit of all the easily observed planets, and Kepler found that no combination whatsoever of uniform circular motions, the cornerstone of astronomy since Ptolemy, kept faithfully even by Copernicus, could reproduce Tycho's Mars positions. His very best circular model left a stubborn residual error of about 8 arcminutes. A lesser astronomer working with lesser data might have shrugged such a discrepancy off as observational error, but Kepler trusted Tycho's precision absolutely, and he wrote that those 8 arcminutes had pointed the way to a complete reformation of astronomy. That single mismatch between an idealized geometry and a measurement he could not doubt is the engine of this whole story. It forced the abandonment of the perfect circle. Kepler published his findings in 2 stages, and they became his 3 laws of planetary motion. The first law states that the orbit of each planet is an ellipse, a flattened oval, with the Sun at one of its 2 foci, not a circle at all, but a shape that carries the planet closest to the Sun at one point of its path, and farthest away at the opposite one. For the Earth, this ellipse is very nearly a circle. For Mars it is distinctly more elongated, which is precisely why Mars, of all the planets, had exposed the failure of the circle. The second law states that the line joining a planet to the Sun sweeps out equal areas in equal intervals of time, so that a planet must move fastest when it is nearest the Sun, and slowest when it is farthest away. Kepler found this merely as an empirical regularity in the data. Only later would Newton reveal it to be a deep conservation law of nature. And the third law, the harmonic law, which Kepler published a full decade later, states that the square of a planet's orbital period is proportional to the cube of its distance from the Sun. In the elegant units astronomers came to use, years for the time and the Earth-Sun distance for the space, the law takes a beautifully simple form. The period squared is simply equal to the distance cubed. Mars, lying about 1.5 times as far from the Sun as the Earth, should therefore take very nearly 1.9 years to complete an orbit, and that is exactly its observed period. It was the first quantitative relationship in the whole of astronomy to link the sizes of different orbits to one another, and it was the empirical seed from which Newton would, in time, extract the very law of gravity. For Kepler's laws described, with wonderful precision, how the planets move, supplying the reason why would be the achievement of the next 2 generations. While Kepler reasoned from Tycho's numbers, Galileo Galilei opened a wholly complementary front, that of direct observation, with the newly invented telescope. Hearing in 1609 of a Dutch spyglass, Galileo swiftly built improved versions of his own, reaching some 20 to 30 times magnification, and in the winter of that year he turned them upon the heavens, rushing his findings into print the following spring as The Starry Messenger. The discoveries were a coordinated assault upon the entire ancient cosmos. The moon, he found, was not a smooth and perfect sphere at all, but a rugged world of mountains and valleys, whose shadow lengths he even used to estimate their heights, proof that the heavens were made of ordinary, imperfect matter like the earth. And the soft band of the Milky Way, turned to under his lens, dissolved into countless faint stars, implying a universe immeasurably vaster than the tidy closed sphere of the fixed stars. But the 2 most decisive discoveries were yet to come. Galileo found that the planet Jupiter was attended by 4 moons of its own, wheeling about it night after night, a plain and undeniable proof that a body other than the Earth could be a centre of motion, striking directly at the claim that everything in the heavens must circle our world. He saw dark spots blemishing the face of the supposedly incorruptible Sun, and most important of all, he observed that the planet Venus passes through a full cycle of phases, from a thin crescent to a nearly full disk, accompanied by a great change in its apparent size. In the old Ptolemaic system, where Venus forever lies between the Earth and the Sun, it could only ever show a crescent. A complete set of phases was possible only if Venus in truth orbits the Sun. The phases of Venus did not, by themselves, prove Copernicus right over Tycho, but they conclusively killed the pure Ptolemaic model. Galileo's telescope had converted heliocentrism from an abstract calculating device into a claim about physical reality, and that physical claim is precisely what brought Galileo into collision with the Church. In 1616, the Roman Inquisition examined the doctrine and judged the proposition that the Sun is the immovable center of the world to be formally heretical. Galileo was instructed neither to hold nor to defend it. For over a decade he largely complied. But in 1632 he published his Dialogue concerning the two chief world systems, a work that argued the heliocentric case with such persuasive force, and which placed a favoured argument of the Pope himself in the mouth of a slow-witted character, that it was read, unmistakably, as a defence of Copernicus, rather than the neutral comparison its licence had required. Galileo was summoned to Rome and tried in the summer of 1633. Found vehemently suspect of heresy, he was compelled to kneel and read aloud an abjuration, renouncing the motion of the earth, and he was sentenced to house arrest, which he served at his villa until his death in 1642. The episode has often been mythologized, but its scientific lessons are quite concrete. First, the evidence available in 1633 was, in truth, genuinely incomplete. No stellar parallax had yet been detected, no annual shifting of the stars, as the Earth supposedly swung around the Sun, and that absence was, on the data of the day, a perfectly legitimate objection to a moving Earth. Second, and more deeply, the affair reveals that the very authority to adjudicate claims about nature was, at that moment, bitterly contested between the new observational reasoning on the one hand and doctrinal tradition on the other, and that the eventual triumph of observation was neither immediate nor in any way guaranteed. The institutional freedom that astrophysics now takes entirely for granted, the plain right of a measurement to overturn a model, however cherished, however comfortable, was won in part in conflicts exactly like this one. Kepler had the laws, Galileo had the mechanics of falling bodies and of inertia. What was still missing was the single unifying cause. Isaac Newton supplied it in his Mathematical Principles of Natural Philosophy of 1687, a monumental project prompted and generously financed by his friend Edmund Halley. Newton's law of universal gravitation states that every two masses in the universe attract one another, along the line joining them, with a force proportional to the product of their masses, and inversely proportional to the square of the distance between them, so that doubling the distance quarters the pull. But the true genius of the Principia was not merely to assert this force. It was to prove that this one force entails all three of Kepler's laws. Together, an inverse square attraction toward a central point yields, of mathematical necessity, elliptical orbits, Kepler's first law. Any central force at all produces the sweeping of equal areas, Kepler's second, and the inverse square dependence specifically and uniquely reproduces the harmonic third, and Newton's version of that third law carried a marvelous gift within it. Hidden inside the constant of proportionality was the mass of the central body itself. Measure a planet's period and the size of its orbit and you can weigh the star that it circles, you can, quite literally, weigh the heavens. The very same force, Newton showed, governs the fall of an apple from a tree, the orbit of the moon about the Earth, the rise and fall of the ocean tides, and the long, sweeping paths of the comets. And Halley used Newton's own methods to predict the return, in 1758, of the great comet that has borne his name ever since. The Newtonian synthesis is the very moment at which astronomy became a deductive physical science, a mere handful of mechanical principles applied universally across all of space, generating the entire observed choreography of the sky. Yet for more than a century after Newton, astronomy remained a science of positions and of motions, of where the bodies are and how they move. The question of what the stars were actually made of seemed permanently, hopelessly unanswerable. As late as 1835, the French philosopher Auguste Comte cited the chemical composition of the stars as his very example of a thing forever beyond the reach of human knowledge. Spectroscopy would prove him spectacularly wrong within a single generation. Newton himself had shown that a glass prism spreads white light out into a continuous band of colours. The decisive refinement came from Joseph von Fraunhofer, a master optician of Bavaria, who around 1814 passed sunlight through a narrow slit before the prism and discovered that the spectrum of the sun is crossed by hundreds of fine, dark lines, standing always at the same fixed positions. He carefully mapped over 500 of them, but their physical cause would remain a complete mystery for 4 more decades. The explanation arrived around 1860, from the collaboration of the physicist Gustav Kirchhoff and the chemist Robert Bunsen, working together at Heidelberg. Burning samples of the elements in Bunsen's nearly colourless flame and spreading the light through a prism, they found that each chemical element emits its own characteristic pattern of bright lines, at fixed wavelengths, an unmistakable spectral fingerprint. And then Kirchhoff realized the crucial thing, that the dark lines crossing the sun's spectrum coincide exactly in their wavelengths with the bright lines emitted by known elements here on Earth. From this he formulated the 3 laws of spectroscopy. A hot, dense body gives off a continuous rainbow of color. A hot, thin gas gives off bright emission lines, unique to the elements it contains. And a cool gas lying in front of a hot source produces dark absorption lines, removing from the rainbow exactly those wavelengths it would itself emit, were it hot. The dark Fraunhofer lines were therefore absorption lines. Light from the sun's dense, glowing surface passes outward through the cooler gas of its atmosphere, and that gas subtracts its own signature wavelengths from the light. So by simply matching the lines, Kirchhoff was able to identify sodium, iron, magnesium, calcium, and other perfectly ordinary earthly elements present in the sun. And the consequence of this was profound and almost philosophical. A star's composition, its temperature, and its very motion are all encoded within its light, and its chemistry can therefore be read across the immense gulf of interstellar space. The technique was so powerful that it at once began discovering brand new elements, here on Earth, by their spectra alone. What Kant had declared unknowable had become, almost overnight, a matter of careful measurement. 2 further advances now supplied the dimensions that spectroscopy alone could not. The first was the long-sought measurement of stellar parallax, the tiny annual shift in a nearby star's apparent position, caused by the Earth's own motion around its orbit, the very shift whose absence had stood as an objection to a moving Earth ever since antiquity. The shift is so minute precisely because the stars are so unimaginably distant. In 1838, Friedrich Bessel at last succeeded in measuring it for a star known as 61 Cygni, which he had chosen for its large proper motion across the sky, itself a sign of nearness. He found a parallax of about 1/3 of an arcsecond, placing the star some 10 light-years away. It was the first reliable distance ever measured to any star beyond the Sun, and at the same time, the first direct geometric proof that the Earth truly does move through space, vindicating Copernicus and Galileo 2 full centuries after their deaths. Parallax also defined astronomy's fundamental unit of distance. A star whose parallax is exactly 1 arcsecond is said to lie at a distance of 1 parsec, about 3¼ light-years. The second great advance was the Doppler effect. In 1842, Christian Doppler proposed that motion along the line of sight must shift the observed frequency of any wave. And for light, this means that an approaching source has its spectral lines shifted toward the blue end of the spectrum and a receding source shifted toward the red. And because Kirchhoff's spectral lines occur at precisely known rest wavelengths, the measurement of their displacement yields directly the velocity of a star, toward us or away from us. Together, then, parallax and the Doppler shift gave astronomy a quantitative grip on the full 3-dimensional positions and velocities of the stars, the very foundation upon which the 20th century would later build its discovery of the expansion of the universe itself. Spectroscopy, joined now to distance, turned the old descriptive astronomy of positions into something entirely new, astrophysics, the application of physics to determine the actual nature of the celestial bodies. The pivotal figures were the English amateur William Huggins and his collaborator and wife Margaret Huggins, working from a private observatory at their home in London. From the early 1860s, they attached a spectroscope to their telescope and obtained the first detailed spectra of the stars, showing that the bright stars display absorption line spectra of exactly the same kind that Kirchhoff had analyzed in the Sun, and containing the very same familiar elements, hydrogen, sodium, iron, calcium, and the conclusion was momentous and simple and grand. The stars are suns. They are made of the same chemical elements as the earth beneath our feet, and they obey the same physical laws. Then, one night in 1864, Huggins turned his spectroscope upon a planetary nebula and saw not the continuous rainbow of unresolved starlight, but only a few isolated, bright emission lines. This proved at a stroke that some of the so-called nebulae are not distant clusters of stars at all, but clouds of glowing gas settling a long and stubborn debate about their true nature. And in 1868, Huggins made the very first measurement of a star's radial velocity, detecting a tiny shift toward the red in the hydrogen line of Sirius and inferring from it the star's slow motion away from us, the first application of Doppler's principle to a star, and a foretaste of the kinematic astronomy to come. But the single most dramatic vindication of the new science came in that very same year. During the total solar eclipse of 1868, the French astronomer Pierre Janssen observed the spectrum of the sun's flaming prominences and recorded there a bright yellow line that corresponded to no element then known. The English astronomer Norman Lockyer, working quite independently, saw the very same line late that year, and concluded together with the chemist Edward Frankland that it must arise from an element present in the sun, but as yet entirely unknown on the earth. They named it helium from the Greek word for the sun, and helium would not be isolated here on Earth for nearly 30 more years. Spectroscopy, more vividly than any argument ever could, had discovered a constituent of the cosmos before chemistry could so much as lay a hand upon it, and with that astonishing feat, astrophysics became, at last, a fully independent science. The rising flood of stellar spectra soon demanded organization, and the great cataloguing effort took place at Harvard, under Edward Pickering, who employed a remarkable team of skilled women as his computers. Chief among them, Annie Jump Cannon rationalized the whole classification into a single temperature-ordered sequence of spectral classes, O, B, A, F, G, K, and M, running all the way from the hottest blue-white stars down to the coolest deep-red ones. Cannon classified the spectra of over 350,000 stars, entirely by eye, with an extraordinary speed and a consistency that astonished her colleagues. The sequence was plainly physical. It clearly tracked something real and continuous about the stars themselves, but why the patterns of lines should change so smoothly along it remained, for the moment, quite unexplained. The explanation, when it came from the new statistical physics. In 1920, the Indian physicist Meghnad Saha derived an equation giving the degree to which a gas becomes ionized, its atoms stripped of their electrons, as a function of its temperature. Saha showed that the strength of any particular absorption line depends overwhelmingly upon temperature, because it is temperature that controls how many atoms sit in the one specific state capable of producing that line. And so the great Harvard sequence from O to M is revealed to be, first and foremost, a sequence of temperature, not of composition at all. The apparent chemical diversity of the stars was largely an illusion, the same essential material displaying utterly different spectra, merely because it burned at different heats. This single insight underlies what is still the most important diagram in all of stellar astronomy. Working quite independently, Ejnar Hertzsprung and Henry Norris Russell each plotted the luminosity of the stars against their temperature and found that the stars do not scatter randomly across the plane at all, but gather into a few well-defined regions. A great diagonal band, the main sequence, running from the hot and brilliant down to the cool and faint, a separate group of cool but enormously luminous red giants, and a huddle of stars that are hot yet strangely dim, the white dwarfs. The Hertzsprung-Russell diagram became, and remains to this day, the master tool for understanding how stars are built and how they age, a single plot upon which a star's mere position encodes its temperature, its brightness, its size, and its very stage of life, and the whole long arc was finally completed by Cecilia Payne. In her doctoral thesis at Harvard in 1925, she applied Saha's theory of ionization rigorously to the Harvard spectra, and arrived at a truly startling conclusion, that the stars are composed overwhelmingly of hydrogen, with helium the next most abundant, and all the heavier elements present only in the faintest traces. This flatly contradicted the settled belief of the day that the sun and stars had compositions roughly like the Earth's, and under pressure from senior astronomers, Payne was persuaded to describe her own hydrogen and helium abundances as almost certainly not real. Within just a few years, they were confirmed as fundamentally and profoundly correct. Her thesis closed the very arc this chapter has traced. It took up Kepler's geometry, Galileo's optics, Newton's mechanics, and the spectroscopy of the 19th century, and from them all deduced the actual substance of the stars, that the universe is built principally from the very lightest element of all, and that single fact would prove central to everything that was to follow, to the physics of the atomic nucleus, and to the science of the cosmos itself,